Alright, welcome back. Now we're going to be talking about ozone in the Earth's atmosphere. And ozone can be a tricky topic for people because the word is often used incorrectly in our day-to-day life. Ozone is not a place, like you don't fly an airplane through the ozone. Ozone isn't a layer. You may have heard of the ozone layer. That's a thing. Ozone, though, is a material. It's a gas. You can have a sealed beaker full of, a sealed jar full of ozone or something like that, okay? It's a material. It's a gas. And the strange thing about ozone is what a paradox it is. Because ozone, on the one hand, is absolutely essential to life on Earth, as you're going to see, but it's also a nasty, awful pollutant. So what we want in our atmosphere is to have ozone at the right place, namely way up high in the ozone layer, which is about 25 kilometers above the surface of the Earth, and not down here at the surface where it's a byproduct of like the exhaust from motor vehicle, when they make pollutants and so on. This is a real problem with ozone. We both need it and we don't want it. But we want it up in the stratosphere. It's going to turn out to be necessary for life on Earth. So, just to be clear about this, ozone is a gas. It happens to be a variable constituent of the Earth's atmosphere, just to use terminology from our first lecture. Remember, a variable constituent means that the amount of it in the Earth's atmosphere varies either from place to place or height to height or from time to time. Well, it turns out there's a lot of ozone in some parts in the atmosphere, namely the ozone layer, and virtually none in other parts of the atmosphere. As it happens, ozone is a form of oxygen. It is in fact O3, meaning that it is 3 oxygen atoms hooked together to make one ozone molecule. That's in contrast to the kind of oxygen that you and I need in order to breathe and so on. That's called diatomic oxygen. That's O2, 2 oxygen atoms chemically attached to each other. So we have O2 and we have O3. Now O2, oxygen, ordinary O2, the kind of stuff we breathe, makes up about 21% of the Earth's atmosphere. There is plenty of them. Ozone molecules are measured on the order of parts per billion in the Earth's atmosphere. There's very little ozone in the Earth's atmosphere. Ozone molecules are precious and few. Even in the ozone layer, there isn't very much of ozone. And of course, well, it's something few and far between, and it is necessary for life on Earth, as you're about to see. This is a serious problem if we find some way to damage the amount of ozone in the Earth's atmosphere, but you know where we're going with this, the ozone hole and things like that. But before we do that, we actually do need to talk about how the atmosphere makes ozone. Ozone is produced, probably unsurprisingly, from ordinary oxygen atoms, ordinary oxygen molecules, O2 molecules. If you start off with just 3 ordinary O2 molecules there, and you hit one of them with a little bit of ultraviolet radiation from the sun. Now, before we get any farther on that, ultraviolet radiation from the sun gives off a lot of different types of radiation, as we're going to learn later in this module, one type of which is ultraviolet radiation, or UV radiation. And UV radiation is bad stuff. This is the stuff that causes sunburns and skin cancer, it causes damages to crops, it causes mutations, and so on. In general, ultraviolet radiation is a very bad thing. So, ultraviolet radiation can be absorbed by oxygen. When it hits O2 molecules, it can be stopped. The photon of ultraviolet radiation can hit that atom, and instead of continuing down to the surface of the Earth and causing skin sunburn or something like that, it can use that energy to burst apart, as I show in step 3 here, the oxygen molecule into 2 separate just oxygen atoms. Now, to be candid, oxygen molecules are not very good at that. Just regular O2 molecules are not very good at absorbing ultraviolet radiation. But there's so many of them up there in the Earth's atmosphere, because, I mean, the whole atmosphere is like 21% oxygen. They're going to be able to do this sometimes. Any given photon of ultraviolet radiation from the sun will sometimes will eventually hit an oxygen molecule and be used to break that oxygen molecule up into 2 oxygen atoms, which will zip around the atmosphere and fairly quickly find 2 more oxygen O2 molecules and just chemically hook onto them to make 2 ozone molecules. So you took 3 O2 molecules and added some ultraviolet radiation, and you got 2 ozone molecules. Excuse me. Look what it did. The creation of these 2 ozone molecules took ultraviolet radiation and stopped it, right? That was ultraviolet radiation that would have otherwise made it to the ground but didn't make it to the ground, and took 3 oxygen O2 molecules, which we have plenty of, and turned them into 2 ozone molecules, which are precious and rare. Hey, that's great! This is a nifty little reaction for producing ozone. So the source of ozone is just the breakup of ordinary oxygen atoms by the absorption of ultraviolet radiation, which, hey, we got plenty of those oxygen molecules out there. We don't have 21% of the Earth's atmosphere. There's plenty. Go nuts. Make some ozone out of them. Good thing, too, because that ultraviolet radiation, we don't want that stuff making it to the ground. We wouldn't have, life on Earth wouldn't exist if it were all that ultraviolet radiation was making it to the ground. But, okay, if this process is creating ozone, and the sun just keeps giving off more and more ultraviolet radiation, apparently there's a way also to destroy ozone, otherwise we just keep building more and more ozone in the Earth's atmosphere. So apparently there's some process that also destroys ozone. Well, let me illustrate how that works. Here's 2 ozone molecules. Now, they're both O3 molecules there, and let's say they each got hit by some ultraviolet radiation from the sun. Now, ultraviolet radiation comes into the Earth's atmosphere. To be candid, there aren't that many ozone molecules out there, but every ozone molecule is super duper good at absorbing ultraviolet radiation. If that photon of ultraviolet radiation even comes close to that ozone molecule, he's going to suck it up, and he's going to use that energy that comes from that ultraviolet radiation to burst that ozone molecule apart into an oxygen molecule, O2, and 1 free oxygen atom, which will quickly find each other and bind up, and you'll end up getting 3 just regular O2 molecules. So you have started off with 2 ozone molecules, you added some ultraviolet radiation, and you ended up with 3 regular, ordinary oxygen molecules, which we have plenty of. So the sink of ozone in the atmosphere, what is actually destroying ozone in the Earth's atmosphere, is also destruction by absorption of ultraviolet radiation. Notice then both producing and destroying ozone molecules in the atmosphere in this perfectly natural reaction, it's called the Chapman reaction for what it's worth, is absorbing, it's being powered by ultraviolet radiation. And both processes keep ultraviolet radiation from reaching the ground. Sure, it's possible still to get cancers, skin cancer. Sure, it's possible to still get, excuse me, sunburns and so on. But very little ultraviolet radiation is making it to the ground. Can you imagine if most of that was making it to the ground? It wouldn't be possible to have life on Earth. Each individual oxygen O2 molecule is frankly not that good at absorbing ultraviolet radiation, but there's so many of them out there that somebody's going to get lucky. One of those oxygen molecules is going to get lucky and absorb some ultraviolet radiation as it's passing, and then use that to create some ozone molecules. Ozone molecules, on the other hand, are not all that good. I mean, there aren't that many of them out there, but they're super duper good at absorbing ultraviolet radiation. So, a photon of ultraviolet radiation just has very little chance of making it through the Earth's atmosphere with this combination of ozone and oxygen in the Earth's atmosphere. Now, as it happens, the place where this works best is about 25 kilometers above the ground. Why that is where it works best is a complicated problem that you don't need to know for the test. It's a complicated matter of combination of how high up in the atmosphere you are and how thick the atmosphere is at that location and how much oxygen there is and so on. That's not terribly relevant. But the greatest concentration then of natural ozone in the Earth's atmosphere is in this so-called ozone layer, and it's about 25 kilometers above the ground in a part of the atmosphere called the stratosphere. Now, later in this module, we're going to learn about the different layers and levels of the Earth's atmosphere, but for now, it's enough to know that that layer of the atmosphere is called the stratosphere. The ozone layer is part of the atmosphere called the stratosphere. That is starts about 11 kilometers above the ground. Below about 11 kilometers is a part of the atmosphere where we live called the troposphere. And in the troposphere, there shouldn't be really any natural ozone. Now, as it happens, of course, we've discussed the fact that pollution can create ozone, and then that can be a problem. But for now, we're talking about the natural situation where there should only be ozone up in the stratosphere in a concentrated layer called the ozone layer. Now, let's not go nuts, though. Even in the ozone layer, we measure ozone in terms of parts per billion. There's not that much ozone up there. So just to kind of spell out the details there, the ozone layer, it's centered at about 25 kilometers above the surface of the Earth. excuse me, I had forgotten that I had actually even had a slide that said specifically, even there's very little ozone. The total amount of ozone in the Earth's atmosphere is surprisingly small. And this ozone layer is protecting the Earth from the dangerous ultraviolet radiation that the sun gives off. Without an ozone layer, there's just no way we could have life on Earth. Which, of course, means, you know, we must have found a way to mess with this because we are worried about the ozone layer and so on. That's what we'll learn about in the third part of the lecture, but for now, let's answer a couple more questions. Question 6. Ozone is necessary for life on Earth because it keeps blank from reaching the surface of the Earth. Smog, diatomic oxygen, ultraviolet radiation, or infrared radiation. Which of these is the right thing that's being blocked by ozone molecules in the atmosphere? Make a choice from those 4 options and get a little feedback before you move on to question 7.